Today's a great day. Every day is a good day when you can do calculus, but today's a great day. So we start, as we often do, with a problem. And this problem came from the person who's actually in the office next door to me. And I like it. It's a good one. So here we go. The doctor, and you're probably thinking, the doctor? Doctor who? Exactly. Has discovered that the Daleks have broken the timeline. In particular, that the timeline now has a gap. And if you were to model it as a piecewise function. So we see the following. That time was flowing pretty well. So it looked like this. We had time. And then, all of a sudden, there's this gap. So here's 0 and here's 1. And it's broken the timeline. Now this is catastrophic and would mean the end of time if nothing is done. Using the TARDIS, and of course we all know that TARDIS stands for time and relative dimension in space, the Doctor will be able to bridge the gap for 0 less than or equal to t less than or equal to 1 with the curve of the form at cubed plus bt squared plus ct plus d, where a, b, c, and d can be set inside the TARDIS. There's various knobs and levers and dials. There's all sorts of stuff. Now, in order to make sure that time will flow through the stopgap, the Doctor must not only make sure that the curves line up, but that the transition is smooth. Now, smooth is a word you might hear a lot. Smooth is a nice way to say differentiable. So it's a flat. There's no like absolute value of x. That's something that's not smooth. There's that little, where the curve, got to be smooth. So the question is, how should the Doctor set A, B, C, D to save the timeline? So really what's happening here in this problem is we want to come up with something to go in the middle. So we already have the parts below 0 and the part above 0. So the question is, what's the part that goes in, not above 0, above 1. The question is, what do we put in between? So at cubed plus bt squared plus ct plus d. And that's if we're between 0 and 1. So, in some sense, we can say, oh, well, we talked about this sort of thing before. We said, hey, if I want the function to be continuous, I just have to find something that will, line up. Now, of course, if we just want continuous, we could just say, oh, just put in this line segment there. And there you go. The problem is, this won't be smooth. Because if you look, at 0, for example, it's coming at a 45-degree angle, and then boom, immediate turn. No, not going to work, not going to work. So we can't just line things up. So what do we need? Well, we need a couple of things to happen. We need it to be continuous, and that means that everything does line up, and this was at 0 and 1, and we need it to be differentiable. And the good thing, I can't spell the word differentiable. Abbreviate, diff. It has to be differentiable at 0, 1. All right. Now, if you think about it, that really says that we have 4 things that need to be true. Because there's continuity at 0, continuity at 1, differentiability at 0, differentiability at 1. And we have 4 things to play with. A, B, C, and D. That's a good. So we have 4 things to play with and 4 conditions that need to be met. That oftentimes means, okay, we just have to find the right combination. Now let's think about what has to be true. Let's deal with continuity. Now we'll just simplify the logic because we're to the point now where we're comfortable with what's going on. So in order for it to be continuous, the pieces have to match up. So that says whatever I'm getting from the left-hand side as I go to 0 should match from the right-hand side. So from the left-hand side, you just plug 0 into here, which would give you 0. And that better match up with what would happen if you plugged 0 into this new form. Well, 0 is a very convenient number. You're going to get 0 plus 0 plus 0 plus d. Whoa. We've already solved 1/4 of the problem. That's pretty good. All right, so this will assure that we're continuous at 0. For 1, again, we have to make sure that the continuity from one side, say t minus 1, you'd plug in t equals 1. that has to match the continuity, that has to match with the other side. So you plug 1 into the other side. So that would be A plus B plus C plus D. And, all right, so this is the continuous. Continuous at 0, continuous at 1. Now for differentiability, what we do is we take derivatives. Now derivatives really are asking what happens locally. So when you have a piecewise function, you can say, look, I can look at my differentials, or the derivatives, at each part. Because I only really care what happens nearby. So each part I can think of as its own thing. So, what's the derivative of t? Yeah, that one's pretty good. And I'm going to be a little bit pedantic here. Hopefully that's a good word. But I'm going to say if t is less than 0. The equal 0 is going to be a little bit tricky, so I don't want to claim that that's true at 0. But, all right, so it's 1 if I'm below 0. What's the derivative of t minus 1? Yeah, it's also 1. It's a line. It's easy to take derivatives of lines. Just grab their slopes. So if I'm above 1, it's 1. And then if I'm between, well, we should be able to do this one. We talked about the derivative of the cube last time. We've done derivatives of squares. We've done derivatives of lines. So we'll skip the limit definition in the interest of time. What is the derivative of at cubed plus bt squared plus c times t plus d? At squared, 2bt plus c. And if you're wondering about that, we'll go into more detail in today's lecture about how you do this. So what needs to be true? Well, before, when we looked at continuity, we said, oh, you just have to have, like, what's coming in from the both sides have to equal each other. For differentiability, it's the same thing. Once you're continuous, then you have to make sure that the slopes line up. So we go through the same process. Well, from this side, we say, okay, the slope looks like it should be 1. If I plug 0 into this formula, then I get 0 plus 0 plus c. So c should be 1. And then on the other side, here at 1, I should say, well, I should get 1. Should equal what happens when I plug in 1. Well, that's 3a plus 2b plus c. So now I can start updating. Well, we've already found 0 equals d, and we found that 1 equals c. So that's good. So let's see what's left. Well, we get 1 is equal to a plus b plus 1 plus 0, which tells us that a plus b had better be 0. Because I can plug in these values. Oh, whoop, no, I screwed that up. This should be 0. You should tell me when I make a mistake. Because I plug in 0 is the value of the function when I plug in t equals 1. Okay, so 0 equals a plus b plus 1 plus d. So a plus b had better equal negative 1. All right. In here, 3a plus 2b plus 1 has to equal 1. So 3a plus 2b had better equal 0. All right. 2 equations, 2 unknowns, and that's the right number of equations and right number of unknowns. So you could do lots of things. For instance, if you multiply the first equation by negative 2, you could say that it becomes minus 2a minus 2b equals 2. And then if you combine, 3a minus 2a is a, and the 2b and not 2b cancel, leaving us with a equals 2. Well, once you know a equals 2, plug it in. 2 plus b should be negative 1, which tells us that b had better be negative 3. And so now we found our parameters. D should be 0, C should be 1, A should be 2, and B equals 3. So that is our answer. And therefore, if we were to go through and set our gap, our little stopgap measure, to be of the form 2t cubed minus 3t squared plus t, this is what's going to save time. And if you were to go and graph it, you'll see it does the following. So it goes up, and then it does a little up and down, and then it's ready to go back again. So it works out, which is good. We want things to work. We like time. We like to keep it. All right, so what's today? Well, today we're going to sort of deal with limits, in that we want to move away from them. See, we like the idea, the intuition of what limits are. Because limits say, hey, if I want to understand what's happening, we like zoom in. So it's like we're doing that pinch zoom, where we keep zooming in and look closer and closer. And that's the idea. Whenever you see that closer and closer, nearer and nearer, smaller and smaller, things like that, that means a limit is going on. So we like the idea of limits. But if it's one thing that we've learned about limits, is that they can be hard. We did some examples in the last few sessions where we had some pretty non-trivial derivatives using limits, and it took a while. So we'd like to be able to still do derivatives, but not have to work with limits. And so what we're going to do is we're going to develop a collection of rules. And these collections of rules are going to allow us to start taking derivatives without having to resort to limits. And the way I like to think of it is we're going to come up with a better user interface. So, no longer do we have to type things in with the keyboard. Now it's just we can point at things and drag, and life will be good. All right. So if we're going to do this, we have to do two things. And what we need are some basic functions. How do we take the derivatives of really simple functions? And then the other thing we need is, how do we take derivatives when things are combined together? So when I talk about things being combined together, I'm talking about things like adding or multiplying or dividing, that type of nature. If we have these two things, our building blocks and our rules for putting things together, then we can take the derivative of pretty much everything. And here's the beautiful idea. With just about 10 simple facts that we're going to develop over the course of the next few sessions, we can take the derivative of pretty much everything that we're going to see for the rest of calculus. So once we get the hang of it, derivatives are actually not so bad. And it's very, very mechanical. But it takes a while to get the hang of it. All right, so what's our basic building blocks? Well, we're going to start with a pretty simple one. If I have a derivative of 1, it's equal to 0. Now this is pretty simple because we've already talked about this idea, which is suppose I have a constant. What's the derivative of a constant? The derivative of a constant is 0 because derivatives are talking to us about change. If we're constant, we're not changing, and therefore the derivative should be 0. And 1, of course, is a constant function. If I have the derivative of x to any power, and I mean any number, x to the k, the derivative of that, you take the k in the exponent. So if it's x to the kth power, bring the exponent down and then subtract 1 from the exponent. So k times x to the k minus 1. Now we can check to see if that matches with what we did before. We did the derivative of x squared. Do you remember what the derivative of x squared was? 2x. Notice the 2 came down, and now it's to the power x to the 1, which is 2 minus 1. How about the derivative of x cubed? We did that. Do you remember what it was? 3x squared, right. Notice the 3 came down. Then it's 1 less than the exponent. We can even do this with just x. Derivative of x to the 1. It was 1, x to the 0, but x to the 0 is a constant. We think of it as 1. I think we even did the derivative of square root of x at one point. What would that be? So people are like, 1 over 2 root x. Wow, okay. Now if you're not sure where that's coming from, I'm running out of space. So derivative of square root of x. Square root of x is a nice symbol, but it's not really useful for calculus. And so when you see a square root, you replace it with a better symbol, better notation. That's x to the 1/2. So the rule says the 1/2 comes down, x to the negative 1/2, because you subtract 1 from 1/2. X to the negative 1/2, well, the negative means it's 1 over, so that's where it comes from downstairs, 1 over x to the 1/2, so that's where that square root of x is x to the negative 1/2. So all the derivatives we've done so far follow this rule, and we're going to show you how the rule works for some special cases. And the last building block for today, not the last rule for today, but the last building block, is the exponential function. If I have e to the x, and I take the derivative of e to the x, I'm going to get e to the x back. So e to the x is this really magical function, which says that if I look at the change, it's equal to the function itself. If you think about the graph of e to the x, it kind of makes sense, because the graph of e to the x looks roughly like that. And if I'm over here, what's true about the change? It's fairly small. But as I move over here, what's true about the change? It's getting larger. So it's going from a small change to a larger change as I move along. And it turns out that e to the x function is that really good sweet spot where the amount of change is equal to the value of the function. And essentially, it's the only function with this property up to scaling. Because of this function, by the way, if you don't like e to the x now, when you get to differential equations, you're going to love it because everything gets an e to the x. It's like, this problem gets an e to the x. That problem gets an e to the x. Every problem gets e to the x. So embrace it now. Embrace it now. All right, so now we have these rules. So let's just make sure we paid attention. Okay, so what's the derivative of e to the 100? Well, somebody said 0. That's actually the right answer. I will say a lot of people are like, wait a second, e to the 100, I should be using this rule here. It's e to something. But what's the difference between e to the 100 versus e to the x? Yeah, this one's actually a constant. This is a function which varies. E to the x is varying, but e to the 100 is not. So be careful. We throw things in like this for fun to see if you're paying attention. But of course, you pay attention. You come to class. We can't trick you. All right. How about the derivative of x to the e? What would that be? Well, which rule are we in? We are not in this e to the x rule. We're in the x to the power rule. So the x to the power rule says the e comes down, and then you subtract 1 from the exponent. So make sure you know which rule you're in. All right. Well, here we go. Let's talk about the derivative of x to a power. Now there's a couple of things that we've seen. We know, for instance, that if I have z squared minus x squared, that's a difference of squares, so I can write that as z minus x times z plus x. That's not too surprising. And I think on one of our quiz problems, we even saw a difference of cubes, which said if you had z cubed minus x cubed, you can write this as z minus x times z squared plus zx plus x squared. But you can keep going. It turns out you can talk about any difference of powers. So if I have z to the n minus x to the n, and here I'm going to assume n is a whole number, and I know that you want to have arbitrary number, but right now I'm thinking of n as like 1, 2, 3, 4, so forth and so on. One of the counting numbers. So it turns out that z to the n minus x to the n can be written as z minus x times this long expression, where you have z to the n minus 1 plus z to the n minus 2 times x plus plus x to the n minus 1. Now what you should think about is the z powers are going down. So you start at n minus 1, the next one is n minus 2, and it goes all the way down to the end where you get 0. The x powers are going up. X to the 0, x to the 1, all the way to the end where you get x to the n minus 1. And that's what's happening. So as one goes up, the other goes down. And it's easy to verify this is true because you just do the multiplication. Z times z to the n minus 1 is z to the n. And then what happens is if you compare this term, z times z to the n minus 2, x would be z to the n minus 1 times x. You subtract z to the n minus 1 times x. So what happens is you get tons and tons of cancellation, except at the very start and except at the very end. So that's why that works. So how do we finish off the check? Well, remember that there were two variations for derivative, and this is that rare exception when I'm going to use the other kind. So you can either talk about as h goes to 0, or you can talk about as z goes to x. They both work. So if I want to take the derivative of x to the n, where I'm thinking of this as my function f of x, that's the limit as z goes to x of f of z minus f of x over z minus x. Okay, that's our limit as z goes to x of z to the n minus x to the n over z minus x. And you can see what's going to happen. We know how to rewrite this expression, z to the n minus x to the n. So we replace it, and we get to cancel off the z minus x. So the z minus x's cancel. What you're left with is this long expression. And there's a lot of terms. There's a total of n terms here. But now you say, okay, what's happening? Z is going to x. So the first term will get x to the power n minus 1. The next will be x to the n minus 2 times x, which is again x to the n minus 1. And that's going to be true all the way to the end. Each one of those will become x to the n minus 1. There's n terms altogether, so you get n to the power x to the n minus 1. All right. Now, the bottom is being cut off, but what it's saying is that this handles it for a lot of cases. The remaining cases will follow from what we do later on, but this is good enough for what we need for now. Okay, so that's our x to the power k discussion. Now let's talk about the exponential. Well, if we're going to talk about the exponential function, we have to start with e. So one of the ways that people often get introduced to e is through the idea of compound interest. And what that means is you might have money you deposit, and let's say you have a very generous bank, 100% interest rate. So we know you put money in, they'll give you money back. So if you, depending upon how often you get that interest compounded, you might have different amounts at the end of the year. So for instance, you might say, look, I put in $1, but if they only give you interest once over the course of the year, at the end, you'll get $2 back. But on the other hand, you might say, well, wait a second, why don't you just give me interest twice over the course of the year? So, so essentially give me 50% in the first 6 months and 50% in the second 6 months. And if you do that, you work it out, you get 2 1/4. Now, the reason it went up is you have interest building on interest. And you're thinking, whoa, I made more money. Okay, well, let's not do it twice a year. Let's do it 4 times a year. You're like, no, I want more money. 8? No. I want all the money. Okay, so the idea is, okay, well, let's do it all the time. Continuously compounding. And if you do that, what you're looking at is if you think about n as how many times you want to compound, you'll get 1 plus 1 over n to the nth power. And you say, I want n to keep getting larger and larger. N goes to infinity. It turns out that you're not going to make infinite money. It goes to a number. It's a nice number, and we could call this number e. And if you work it out numerically, it's 2.718281828. Now, normally you just need to remember about the first couple of digits. I like to remember 2.71828 because there's sort of a chant that goes like this. Come on, exponentiate, 2.71828. Right? There's also one for pi. Do you know the one for pi? It goes, cosine, secant, tangent, sine, 3.14159. Wow. Okay, all right. Maybe you don't know those. But the thing is that these are not, if you just remember the first few digits, that's almost always enough. 2.71828. Okay. So what are we going to do? Well, we understand the idea of limits. We say, all right, well, what does this mean? It says that if we let n be very large, we get the following. So I'm going to let n be large, and I'm going to call h 1 over n, just for convenience. So instead of saying 1 plus 1 over n to the nth power, I can say 1 plus h to the 1 over h. And I say, well, if I'm large, it's about e, because that's what limits say. Limits are saying it's getting closer. So if the limit as you go to infinity goes to e, then it's getting close to e. Now I'm going to raise both sides to the power h. It says that e to the h is about 1 plus h. Okay. Rearrange that, and you get the following. It turns out that e has another wonderful property. If you take e to the power h, where h is a very small number, you subtract 1 and you divide by h, you get something which is close to 1. And when we say you're close to 1, you actually get closer and closer as h is getting smaller and smaller. Because h getting small here is the same as n getting large there. So you're going towards your various limits. And once you understand that, then the rest of it's very straightforward. So here we go. So the derivative of e to the x, well, now my function is e to the x. So that's f of x plus h minus f of x over h. E to the x plus h is e to the x plus h minus e to the x. Now, what can you do to e to the power x plus h? What can we do? Well, that addition in the numerator, addition in the exponent becomes multiplication. So it becomes e to the x times e to the h, which means that both the terms have e to the x inside of them. So if both the terms have e to the x, you can pull it out. It's a constant as far as h is concerned, because the limit is an h limit. So e to the x can pull all the way out in front. So I have e to the x times the limit as h goes to 0 of this other expression, e to the h minus 1 over h. But we know that this part goes to 1. And therefore we get e to the x back. All right. So the derivative of e to the x is e to the x. And it's very nice. It turns out that e is this really cool number. And any other number, like 2 to the x or pi to the x, pi is a cool number. It's a more complicated answer. So e hits just that nice sweet spot. All right. So those are our basic building blocks. The next thing we want to talk about are the rules for putting things together. So the first thing to know about putting things together is that derivatives are what we call linear. They're linear operators. And to say something is linear means two things. You can pull out constants, and you can break up over addition. So the derivative of a constant times f of x is that constant times the derivative of f of x. And if I have a derivative of two things being added, f and x plus g of x, I can take the derivative separately and add the results. Derivative of f of x plus the derivative of g of x. So this is a really nice rule. It says, hey, look for ways to break things into smaller parts. And we work on each part separately. So let's assume all the rules hold. We haven't justified these, but we'll do that in just a few moments. So assuming that these rules hold, let's take this derivative. 5x to the 12th minus x cubed plus square root of x plus 3 over x plus 17e to the x plus pi squared. All right. So the first thing we're going to do is we're going to apply the fact that our derivative is linear. Because we see these additions and subtractions. Addition and subtraction says, hey, I'm trying to combine different parts together. So the derivative of 5x to the 12th, what we can do is we can say, well, that's the derivative of 5x to the 12th. And we don't do this all the time, but we're going to do it. This time we're going to really break it down. Minus the derivative of x cubed plus the derivative of square root of x plus the derivative of 3 over x plus the derivative of 17e to the x and plus the derivative of pi squared. This, again, is a step which, in the future, we're almost never going to write this down, but we're always going to think about it this way. So we're going to write it down this time just to sort of say, okay, and then this is how I think about it. So I'm using the fact that I can break up over addition. And subtraction is essentially the same as addition. The other thing I can do is pull out the constants. So this is 5 times the derivative of x to the 12th minus the derivative of x cubed plus the derivative, and what do we do with square root of x? X to the 1/2. We make it calculus friendly. What do we do with this? Well, the 3 comes out, but what do we do with this 1 over x? What does it become? X to the negative 1 plus 17 times the derivative of e to the x. And here I can actually pull out a pi squared and be left with the derivative of 1. So I'm pulling out all the constants. So now I'm using the other fact that constants pull out. And now we just go through one by one. All right, derivative of x to the 12th. 12x to the 11th. Derivative of x cubed. 3x squared. Derivative of x to the 1/2. We talked about that earlier. All right, 1/2 x to the negative 1/2. Okay. Derivative of x to the negative 1. Negative 1. The negative 1 comes down. X to what power? Negative 2. Yeah, remember, you're subtracting. And you're like, oh, negative 1, subtract 1. Shouldn't that be 0? No, no, no. Negative 1 subtract 1 is negative 2. Okay. Derivative of e to the x. E to the x. And then plus pi squared times the derivative of 1, which is 0. And now we clean it up. Okay, so this becomes 5 times 12 is 60. X to the 11th minus 3x squared. Then you get plus 1 over 2 square root of x, because the x negative 1/2 means it moves downstairs, and it's the square root, minus 3 over x squared, because that x negative 2 moves it downstairs, plus 17 e to the x, and plus the 0. Now, after you do about 10 or 20 of these, you get to a state where, like, I know that it breaks up, it's nice and linear. You'll oftentimes just skip right ahead, which is fine. And somebody asked me a question the other day, and I think I want to repeat the question. I want to tell you the answer. On this upcoming exam, do we always have to use limits? And the answer is no. You only have to use limits if we explicitly state you must use limits. If we don't explicitly state use limits, please, for your own sanity, don't do it. Be smart. Don't start. So use the rules. Use the rules. So let's just talk about why these rules work. They're actually very simple. And the reason, what it boils down to, I'll go ahead and give away the spoiler. The reasons that derivatives are linear is that limits are linear. In other words, they respect what happens when we do things like scale and multiply. Sorry, scale and add. So if I want to take the derivative of a constant times f of x, then I apply the formula for what the derivative is. And I say, hey, both these terms have the same constant. The constant can pull out. And then what's left is the derivative of f of x. That's it. That's the whole proof. The derivative of f of x and g of x, it's essentially the same idea. It's a little bit longer to write it out, so you don't need to. Just remember the rule. So if I want the derivative of f of x plus g of x, well, you get the f of x plus h and the g of x plus h. Subtract the f of x and the g of x. And the moral is you just rearrange. And what you can say is, I can break this limit into two parts. One of them will be the derivative of f, and one will be the derivative of g. So it works out. All right. Well, let's do some practice. Now that it's easier for us to take some derivatives, we can probably do our questions a little bit faster than we did before. So, find the tangent line at x equals 1 to the curve y equals x cubed plus square root of x minus 2 over e times e to the x. So this function here, this is our f of x. That's how we should think of it. All right, so if we're looking for the tangent line, what pieces of information do we need? Slope and also a point. Yeah. So in fact, anytime you see the word line, you should always think, okay, I need a point and a slope. Let me figure out how to get my information. So let's talk about the point. So we have a piece of the point, 1. So that's our x coordinate. How do you get the y coordinate? Yeah, you plug it in. So you get 1 cubed, which is 1, square root of 1, which is also 1. Then you have 2 over e times e. The e's will cancel, meaning you'll get 2. So 1 plus 1 minus 2 gives us 0. So that's our point. 1, 0 is our point. How do you get the slope? Derivative. So we denote the derivative of y as dy dx, or we could write it as y prime. So y prime, which is dy dx, all right, So we're going to try to do it without doing all the intermediate steps. And we're going to just go through it piece by piece. The derivative of x cubed? 3x squared. Good. The derivative of square root of x? 1 over 2 square root of x. The minus 2 over e, that's a constant, times that by the derivative of e to the x, which is e to the x. So this is what we hope you should get to. It's the point where you feel comfortable enough to just write that derivative down. That's where we want you to be. And with practice, you'll get there. You'll get there pretty soon. All right. Now, is this my slope? No, because the slope should be a number, not a function. How do you get your slope? Yeah, you plug in your value. In this case, you plug in 1. So we're going to look at y prime at 1. All right, well, we get 3 times 1. That's 3 times 1 squared. 1 over 2 times the square root of 1. That's 1 over 2. Then we have minus 2 over e times e to the 1. Well, it's minus 2. So 3 plus a half minus 2 for a grand total of 1 1/2 or 3/2. So this is our slope. So once we've evaluated, we have our slope. We have our point and we have our slope. So we can say that y minus our y coordinate is equal to our slope times x minus our x coordinate. So this is that formula, y minus y naught is equal to m times x minus x naught. And we could, if we wanted to, simplify. For example, it turns out that 0 is 0, so that goes away. And we could multiply this through, so we could say it's y is 3/2 x minus 3/2. And there we go. Find all the x. Oh, wow, all of them. Okay, well, there's a lot of x out there. Oh, wait, go, there's more. So that the tangent lines to y equals x cubed minus 12x plus 17 are horizontal. Well, let's think about this word, horizontal. So what does that mean? If you were sketching in the xy plane and you had something that was horizontal, well, it would look something like this. What's true about a horizontal line? Has 0 slope. So horizontal is secret code for saying slope equals 0. All right, so we know we're looking for tangent lines where the slope equals 0. Now when we say slope equals 0, that's even more secret code because slope is saying the derivative is equal to 0. So we're saying, aha, what the question is really asking is when is the derivative equal to 0? Now, if you phrase it this way, it seems a little bit more straightforward and not so bad. So let's figure out, what is dy dx? Well, what's the derivative of x cubed? 3x squared. Derivative of negative 12x? Negative 12. Derivative of 17 is 0. In fact, you'll notice I could have put any number here and it won't change the answer. And why not? Yeah, see, that 17 is that shift up and down. But see, if I have a horizontal line and I shift, it turns out it's still horizontal. So that's why it won't matter what that 17 is. So the last thing is set it equal to 0. So we need to solve this equation. Well, let's see, that says 3x squared should be 12, or x squared should be 4. So what should be true for x? 2. Aha, plus minus, right. Because, of course, negative 2 works just as well. So it turns out that there are 2 values for x, which we will have a horizontal tangent line for. All right. Our last rule for the day, but not the last part of the day, but our last rule for today is the product rule. Now, let me preface the product rule by saying something very clearly. This is sort of like the rule where it's like, okay, it's no longer what you think. So, what do I mean? We talked about when we add things, and we take the derivative, we just take the derivative of each part and we add. And we said, oh, if you scale things by a constant, take the derivative of each part and then you just scale. But if we're taking the derivative of a product, you can't just take the derivative of each piece. Now, what do I mean? It's tempting to say, hey, the derivative of x squared, right? Well, wouldn't it be cool if I think of this as the derivative of x times x? So there's a temptation to say, maybe I could just take the derivative of each piece and multiply the derivatives together. Now, I put in a question mark here because I don't know yet. Well, let's just check. What's the derivative of x? 1. Still the 1. So that's 1. Well, does that match with the derivative of x squared? It doesn't. So the product rule breaks the, oh, it's easy. So you have to be a little bit more careful. So it is not the case that I just take the derivative of the different pieces and multiply them together. It's not terribly far off. But the way I like to think of it is the following. If I have the derivative of f of x times g of x, I take the derivative of the first times the second plus the first times the derivative of the second. And when I said this is the way I like to think about it, is I say, look, every single piece wants its turn. And so they all get their turn individually in their own part. So it's like, okay, I have f of x and g of x. So first person up is f of x. F of x, you get to go first. It says, fantastic. I'll take the derivative of f of x, and then g of x has to sit and wait. And then I say, okay, now g of x, now it's your turn. It says, wonderful. Now f of x sits, and you take the derivative of g of x. And then you combine them together. All right. So, and anyways, this is just the word of warning. Be careful. Be careful. Just because it's easy doesn't mean it's true. And what this more or less boils down to, the reason why you see this sort of differentiation, is that there is a real distinction in mathematics between multiplication and addition. And when you talk about derivatives, what derivatives boil down to at the end of the day is the ability to add and to scale. And so that's why anything that involves addition and scaling is very compatible with derivatives. But multiplying is not the same as adding. And because of that, that's why there is this distinction. So here is the justification. You know, we don't just want to take their word for it. We want to say, why is it true? All right. Got to brace myself here. Make sure there's enough room. So if I want to take the derivative of f of x times g of x, I do what I always do. I plug it into the definition. Limit as h goes to 0. F of x plus h, g of x plus h, minus f of x, g of x all over h. Now, what I'd like to do is pull this apart. And I can't quite do it here, but here's a great idea. Let's add 0. And the claim is that this expression is the same as the expression above, because if you look, this is what's new. And if you look at it, it's you're add and subtract the same quantity. Now, the first reaction is, okay, I give it to you that this is equal, but why are we doing this? And why that choice? Well, we didn't just add and subtract 0, we added and subtracted a well-chosen 0. What we wanted to do was sort of get something halfway in between this first term, f of x plus h, g of x plus h, and the second term, which is f of x, g of x. And the way we did it, we said, okay, we're going to have, say, one of the terms will have an x plus h, and the other term will have just an x. So it was sort of like the halfway in between. That's where that's coming from, that idea. And now what we can do is we say, I can split this up into parts. So if you rearrange, say you just look at the first two terms. You have an f of x plus h minus f of x. They both have g of x plus h, so you pull out what they have in common. And so if you pull out the g of x plus h, you're left with f of x plus h minus f of x over h. Then the second two terms, you do the same thing. They both have f of x in common, so you pull it out. You're left with g of x plus h minus g of x, and there's this over h still there. Then you take the limits, and you say, aha, some of these are pretty easy. For example, f of x becomes f of x. You probably saw that one coming. G of x plus h becomes g of x. This part, that's the derivative of f prime, And the last part, that's the root of g prime, and therefore you get the result. Now you don't have to remember the justification, but you do have to remember the rule, because this will be used over and over again, many, many times. Many, many times. All right, so let's do a little bit of practice. The derivative of x to the 2/3 times e to the x. So we're thinking of, we have the two parts. The x to the 2/3 is one part. The e to the x is the other part. All right, so we go through. We say, all right, what's the derivative of x to the 2/3? 2/3 x to the negative 1/3. Okay, so that's my derivative of f of x. I'll write f prime. And then what do I do with the e to the x? It's e to the x. That's my g of x. Plus, now the x to the 2/3 stays as is. That's my f. And then I times that by the derivative of e to the x. No, the derivative of e to the x. Aha, no, I'm just kidding. Of course, it is e to the x. Yes. Yes. This is one of the confusing things when you use examples with e to the x, because it throws you off. Is that the function or the derivative? Yes, it is. It is. Oh, okay. Well, that clears everything up. All right. So again, this is it. And you can leave it in this format. If you wanted to, you could do things like factor out what they have in common, but we won't ask you to do that. If we did, let's go ahead. Suppose we did want to clean this up a little bit. What do they have in common? They have e to the x. They also have something else in common. They both have powers of x's. Which power of x should you pull out? And why? No, the answer isn't why, but which power of x should you be pulling out? So there's two choices. There's x to the negative 1/3 and x to the 2/3. The answer is x to the negative 1/3. Why that one? Well, the rule is when you're pulling out powers, you should always pull out the lowest power. What's smaller between negative 1/3 and 2/3? Negative 1/3 is a smaller number, so it's a smaller power. So if you pull that out, in the first entry, well, we grab the x to the negative 1/3, we grab the e to the x, that would leave us with 2/3. In the second entry, we grab the e to the x, there's no constant. What's our power going to be? X to what power? It'll be x to the first power. So it'll be 2/3 plus x. Now, if you're wondering how do you get that, you can think of it in two ways. You can say, well, let me go backwards. I have to multiply it by x to the negative 1/3, and it has to give me 2/3. What would do that? And the answer would be 1. The other way to think about it is say, well, I'm pulling out negative 1/3, subtract negative 1/3 from 2/3. 2/3 subtract negative 1/3 would leave us with 2/3 minus negative 1/3 is 1. All right, the derivative of e to the 2x. Well, we don't know how to handle the 2 yet, but we can think of e to the 2x as e to the x times e to the x, which means we can do a product rule. All right, so we start by saying the derivative of e to the x, which is e to the x, times the function e to the x, plus, now we have just the function e to the x, and we times that by the derivative of e to the x, which is e to the x. Well, the first term is e to the 2x, and the second term is e to the 2x, which means that we'll end up with 2 of these. So, when we take the derivative of e to the 2x, it becomes 2 times e to the 2x. Well, that's interesting. That's interesting. I'm curious if there's something going on there. I suspect there might be. Okay, let's do one last example. Suppose we're given the following. F of 1 is 2, f prime of 1 is negative 3, g of 1 is 1, g prime of 1 is 4, and h of x is e to the x times f of x plus 2x squared times g of x. Find h of 1 and h prime of 1. Now h of 1, that's not so hard, so we just plug it in. H of 1 would be e to the 1 times f of 1 plus 2 times 1 squared times g of 1. So e to the 1 is e, f of 1 is 2, so this is e times 2 plus then 2 times 1 squared, which is 1, times g of 1, which is 1. So we end up with 2 plus 2e. Okay. What about h prime of 1? Well, the thing is, I can't say, oh, h of 1 is 2 plus 2e, let's take the derivative of both sides, because this is not going to be nice. Its derivative of a constant is 0. So we have to take the derivative here. We say, well, what rules do we need? Well, we need to know how to take the derivative of e to the x. We need to know how to take the derivative of a product. We need to know how to take the derivative of 2x squared, and then again, the derivative of a product. So we're going to use a couple of rules here. So h prime of x. So we do come to the first term, because the sum rule says, hey, I can take the derivative of the two parts, and I'll just add the results together. So I take the derivative of e to the x times f of x. I start by taking the derivative of e to the x times f of x, plus, now I take the function e to the x times the derivative of f of x. And now we come to the question, well, what is the derivative of f of x? The answer is it's f prime of x. It's the derivative of f of x. Come to the next part. Derivative of the first, derivative of 2 times x squared would be 4 times x. Times the second, that's g of x. Plus the first, 2x squared, times the derivative of the second, so that's times g prime of x. So that's just a generic formula for h prime of x. Now we plug in h prime of 1. So we would get e to the 1 times f of 1 plus e to the 1 times f prime at 1 plus 4 times 1 times g of 1 plus 2 times 1 squared times g prime at 1. We know these pieces, the f of 1, the f prime of 1, the g of 1, and the g prime of 1, because they're given to us in this problem here. So we're going to have e times 2. So that's 2e. Then we're going to have e times negative 3, f prime of 1. So minus 3e. Plus 4 times g of 1. So that's 4. Plus 2 times g prime of 1. So that's 2 times 4, which is 8. So 2e minus 3e is negative e plus 4 plus 8, which is plus 12. So our answers are h of 1 is 2 plus 2e, and h prime of 1 is negative e plus 12. Good. And there we go. So really this is testing, do we know our rules? And hey, if we have f of x, just say the derivative of f of x is f prime of x. That's not so bad. That's kind of fun. Well, hopefully we'll get to do some more. Let's find out. Stay tuned.